Welcome to episode 6 in this series. This is lecture 6 of Introduction to Proof course, centered around the textbook, A General Introduction to the Art of Mathematics. So today's session was going to go basically in 3 parts. First, we'll talk about what it means when two integers have no divisors in common. We'll see what that says about sort of improving our definition for the rational numbers. And finally, we're going to look at an example of a really, honestly, just a beautiful piece of mathematical proving, a statement that was first proved by Hippasus of Metapontum, who was a member of the Pythagorean Society. So let's get going. Well, what if two numbers have absolutely no factors in common? Well, the first bullet here is basically saying that, look, they're always going to have one divisor in common, even if they have no factors in common. The number 1 itself is always a divisor, so that's on. I hate the way this is phrased. I can't think of a better way to say it, but you have two lists, a list of the divisors of A and another list of the divisors of B. 1 is on both of those lists for sure, so there is a common divisor. It might be bigger than 1. You would hope it is, I suppose, but it doesn't have to be. 1 could be it. So that sometimes is the case. Well, I don't know. Maybe that's a question. Does it actually happen that for some values of A and B, the GCD of AB is 1? Think about that for a second. I say sure. Why not? If, for instance, the two numbers are both prime, that's going to do it. It also happens if the numbers are not necessarily prime. One could be prime and the other not, but the issue is, do their factorizations have anything in common? So if their factorizations have no primes in common, then you'll get a GCD of 1. So there's an example, 33 and 35. Neither of those is a prime number. 33 is 3 times 11, 35 is 5 times 7. But you see how their prime factorizations are sort of disjoint. They have nothing in common. Here's a tougher question. 41,140 and 46,683. Why such a weird thing? Well, I just wanted to give you an example where you can answer the question quickly if you've got a computer to help you, but it probably would take quite a while. You'd have to run the Euclidean algorithm on with this pair of numbers as the inputs, and it would take a little while to do by hand. Again, if you implement it on a computer, it's quick. It's enough. If you look in this Sage worksheet, the first thing I've got in here is I found the factors of 41,140 and the factors of 46,683. This one involves 2, 5, 11, and 17. This one involves 3, 7, 13, and 19. They don't have anything in common. You can do this more directly by just computing the GCD. Sage has a built-in function that does GCD. This worksheet's probably unhooked from the server right now, so it's going to take a little time to initialize. And there, ran it and got 1. Okay, so we'll come back to the slides. Some terminology you need to know. When that GCD of two numbers is 1, we call them relatively prime. You can probably guess why the word prime came in there, because when the two numbers are primes, unless they happen to be the same prime, which would be bad, well, then their GCD a GCD of a number in itself is itself. It's as big as it possibly could be. But if you have two distinct primes, their GCD will always be 1. And this is similar to that. These numbers behave as though they were prime with respect to one another. Anyway, so this idea of relative primality is kind of cool. It gets used a lot in number theory and abstract algebra. Just want to be clear that this is a term that has to have two things to which it's referring. Right? You can't say 7 is relatively prime. You can say 7 is relatively prime to 11, but not. It's not one thing. It's a relationship between two things. It's also a symmetric relationship, right? If A is relatively prime to B, then B is relatively prime to A. So we can switch the order around. Yeah, I think I just said this. They could have two distinct prime numbers, but you know, there are other possibilities. Okay, so why are we bringing this up? Well, it has to do with fractions, actually. You know the concept of a fraction being in lowest form. Some people call it simplest form. Then the numerator and the denominator share no common factors, right? You've canceled off anything that was common between the two of them to make the numbers smaller. So the numerator and denominator will be these sorts of things that are relatively prime. Their GCD will be 1 because they will have no common factors. So here's an example, 186 over 210. There's a fraction. You can tell that it's not in lowest terms because both top and bottom are even, right? So I could definitely divide them both by 2. I think, let's see, 9, that's 15, and this is 3. Yeah, if you add the digits, both of these have digit sums that are divisible by 3, so they're also divisible by 3. That means they're divisible by 6, so we could divide a 6 out of both the top and the bottom, and then we wind up with something 31 and 31 and 35, which are relatively prime. 31 is prime itself, and 35, 5 times 7, doesn't have the prime 31 in it. So let's next see what that has to tell us about rational numbers. So back in 1.1, this is the definition we gave for the rational numbers. And it's pretty decent, but it's got an issue. Some people would not be concerned about this issue, but I think as we think more and more carefully about things like the rational numbers, you should get the idea that this is actually a problem. So what's the problem? We're not taking into account the fact that rational numbers can be written in multiple ways. Like I can have 1 over 2, or I could have 3 over 6, or 500 over 1,000. You know, there's billions of ways, well, infinitely many ways to write a half. And every rational number is like that. If you think about just the number 0 as a rational number, it's going to be 0 over anything at all. Right? So any number could be in the bottom. So we want to improve this definition, but let's think about why. I mean, you know, in a sense, you could say this: when you put set braces around a collection of things, it sort of automatically takes out duplicates. The set involving 1, 1, and 5 is just 1 and 5. The 2 copies of 1, we don't count how many copies there are in a set. So set braces should automatically drop duplicates. Here's the issue, though. How do we know what are the things that are duplicates? We all know that a half is the same thing as 50 over 100, or in the slide, 2/3 and 4/6, they're the same. But it's because we understand the arithmetic of the rational numbers that we know that. I'd like to come up with a definition that didn't have all these dupes hanging around, these duplicate entries, and so we wouldn't have to be concerned about this. And finally, you know, I mean, we're trying to make a usable, precise definition, something we can actually get a handle on in the meaning of rational number while we're trying to do proofs about rational numbers. This is the place to sort out any difficulties. Do it early, or come back and revisit this thing once you realize there's been a flaw and that you need to fix up the definition a little bit. So here's my, actually, I'm still lying to you. There's going to be another tweak to this definition later on in the book, but the final, for now, officially approved version of the rational numbers. Well, there it is. It's just got one thing added on. Excuse me. The thing at the end here that says GCD of AB is 1. It's got the other things we mentioned. It looks like a fraction. They look like fractions of the form A over B. A and B are both integers. B is non-zero. Thought this might be a good time to practice our translating skills. So let's try to parse this thing, this long sentence from the previous slide, with English in parallel. The first 3 symbols were Q, equals, and an open curly brace, which we read as the rational numbers are defined to be equal to, I suppose you could add more words to that if you wanted, the set of all. That's how we refer how we pronounce the opening brace. You just sort of verbally describe what you're seeing here, a over b. Okay, well, fractions of the form a over b. That vertical bar is read as such that. Sometimes people will use a colon in the same position, and it means such that too. Um, a and b are elements of the integers. This could have been written as a as in b, a as in z, and b as in z, but it's a common shorthand to just comma separate a bunch of things that are all in the same set. Oops. And well, what else happened? B is non-zero, b not equal 0, or just say b is, I think it's smoother in English to say b is non-zero, and becomes and. Read GCD of a and b equals 1 as a and b are relatively prime. Okay. Is it worth doing this just one more time so we can do it quickly? So I'm going to come back and do this once more with gusto, as they say. Do it a little quicker so that we get the flow of reading this math as reading these symbols as English stuff. So Q is defined to be the set of all fractions a over b such that a is an integer and b is an integer, b is not 0, and they're relatively prime. Good. All right, so we're on to sort of the really the important piece of today's lecture. Are there irrational numbers? Well, okay. Pythagoras, I think most folks have heard of Pythagoras. He is famous for thinking, an element of his philosophy at least, was that literally the universe was made up of numbers. That is, everything is constituted by mathematics. In the past, people often discussed the Pythagorean society, but more and more often I've noticed people calling it the cult of Pythagoras. And that has something going for it. Really, the Pythagoreans were more cult-like than you would believe. They had a lot of strange beliefs. There's quite a lot of interesting history surrounding Pythagoras. I can name a few things for it. For instance, his society that he founded in Croton in what's now Sicily. That was still part of Greece, Greater Greece at the time. It had some political action, so there was they weren't entirely just all about doing math. He had two different sections to his society. The inner group of people who actually knew all the secret information that they kept, and they literally thought some of their mathematics needed to be kept secret, that they didn't want, this knowledge to get out. They wanted to possess it themselves. There was also an outer society, which I think mostly constituted muscle. They were people that believed in Pythagoras more as a personality than having any interest in mathematics. The names of the two circles are interesting. The outer group was called the acoustomachoi. I'm probably getting it wrong, but I know the Greek root acoustics was in there. And it has to do with sound, right? Acoustics. So I think they were there to be sort of a cheering squad or to make a big noise when necessary. The inner circle were called the mathematicoi. They were mathematicians. Wow, Pythagoras has so many strange factoids around him. This is somebody who lived well before 0 AD in the BCE eras. He everything was sexist at that time. Everything. He didn't believe in that. So there were functioning female members of the inner circle. The first known female mathematician was one of Pythagoras's followers, potentially his wife. And I beg your pardon, but her name is escaping me right now. You could refer to the History of Math archive, which I've touted a few times. The inner circle, at least, of the Pythagoreans were strict vegetarians. That was part of their belief. Uh, I think they thought, in particular, people would sometimes be reincarnated, and if they ate meat, they could potentially be eating a former friend. It is also thought that this is a potential explanation for a strange behavior of Pythagoras's. It's thought that they thought sometimes people reincarnated as bean plants, or it may be because beans look like male genitalia to a certain extent. In any case, Pythagoras wouldn't touch them. He wouldn't go near beans. So when his cult finally got routed by the local authorities in Croton, he was being chased by men, armed men with swords, um, and they encountered a bean field, and Pythagoras refused to cross it. So I think he met his end at that moment. Lots of weird stuff about Pythagoras. It's really good reading if you want to hear some interesting stories. Anyway, back to numbers. For quite a while, up until roughly the time of Pythagoras, people believed that rational numbers were it. That's all we needed to do real stuff. So what we now think of as the real numbers, things that measured physical quantities like lengths, weights, masses. I should say masses, not weights, but back in those days they only did weights. Areas, volumes. There's many other things now, but in those days they would probably have settled with this and maybe a few others. Anyway, they thought all these physical quantities could be expressed as fractions. It seemed to them a foreign concept. Almost it would be saying something against the gods if you thought that a number couldn't be expressed as a fraction. Remember that belief that all is number? You build everything out of the integers, really. And it's easy to see that you can get rational numbers out of the integers, but why would you need anything else, right? Well, it turns out there just is other things, but they didn't know that at the time, and it went counter to their intuition. So today, you guys probably believe in irrational numbers. That's the phrase we use for numbers that are real but aren't rational. I want to make a note that there's no name for that set. We don't have a capital I is equal to the irrational numbers or anything. Just it's the difference between the reals and the rationals, if you like. But anyway, you believe in them because some things are out there like pi and √3/2 that don't have one of these finite length cyclically repeating patterns in their decimal expansion. But if you're honest with yourself, it's likely that you just took somebody's word for that. I mean, you certainly didn't verify it, right? Did you look at all the digits of pi? There's no reason why a repeating pattern in the digits of pi couldn't be 5 billion digits long, right? We haven't really looked at all the digits of pi, so we couldn't necessarily find any repeating pattern that might exist. It's true we certainly don't see repeating patterns in the first reasonably small number of cycle lengths, but who knows? So yeah, we took somebody's word for that. I know I did when I was first looking at these things. But this guy Hypasus, he proved it. At least he did this for √2. √2. So he proved that there was at least one physical length that was not a rational number. And that actually is a physical length. If you imagine a square with unit sides, so 1 by 1 square, the diagonal of that square, you think of it as the hypotenuse of a right triangle with two sides of length 1. Anyway, the diagonal of that is √2. So that's a real quantity. So the measure of a particular length, distance between 2 points, √2 is a real number. He proved that it's not rational. And then what happened? Well, there are multiple stories about and then what happened, but apparently they killed him for it. It may possibly have been a different Pythagorean secret that he gave up. Like, they may have been that they went ahead and accepted the √2 business, but he also blabbed about the existence of the regular icosahedron. And that was a really kind of a big deal to them. I should have had a regular icosahedron here ready to show you. Hang on one sec. Okay, so I just went and procured this toy, which is a really fun thing. I bought this when my kid was like 2 years old. I thought it was pretty awesome then. It's still exciting to me now. It's these plastic frames in the shape of triangles. They actually have other shapes as well, but if you look at them closely, you can see there are little magnets in pockets inside of them. Um, there's something somewhat dangerous about this. If your kid is really vicious or bites into this, he could end up getting one of those magnets inside of him, and that wouldn't be bad. But if you got two of those magnets inside of you, that could be life-threatening. They're very strong magnets, and if they attracted to one another and pinched some piece of your internals together, you could die. So my ex-wife took them away from my son, so he didn't really get to play with them. But the idea is that when they get close enough together, the magnets will rotate in place in those pockets, and they attach. No matter how they're stuck together, they'll make an attachment. So the regular icosahedron is made up out of triangles. That's why this thing is appropriate. I'm just going to bring 5 of them together. That's one corner of the regular icosahedron. 5 triangles meeting at a corner, and you can see that it doesn't lie flat in the plane. It's got a sort of a cup to it. It turns out that you can just keep doing this at each potential corner, make it so that 5 triangles meet. So now I've got something with 2 corners with 5 triangles meeting it. And if you keep going, you eventually end up. I'm not sure this is good use of our time, so I'm going to let you think about this, how to continue. But you can indeed all continue and always put 5 triangles together at a corner, and you end up with a ball that's got 20 triangular faces. People who've played role-playing games are very familiar with this. They call it D20, and it's a 20-sided die. It's a useful thing to have, if you're trying to figure out just how much damage your magical strike is going to do against a dragon. You roll a d20 and you find out. Okay, so he may have given up the existence of the icosahedron, or it may have been they just really hated this proof. There are varying versions of the story, but Hippasus was apparently put to death by the Pythagoreans. One version of it has them all out on a sailboat, taking like a pleasure trip, celebrating something, possibly celebrating this proof. Right? And then they pitch him over because they weren't really in the celebratory mood, really. Okay. This argument that Hippasus came up with is likely the very same one that appears in the books of Euclid, and it was selected by this man, G.H. Hardy, in what I view as just a remarkable, beautiful little book about mathematics. It's about the subject, but it's not trying to teach you mathematics. The book is called A Mathematician's Apology. The man's name was Godfrey Harold Hardy. Nobody called him Godfrey. He was this is conjecture on my part, but I know he was a devout atheist. So he may have not liked that his first name involved the word God. Some very good friends called him Harold, but most people just knew him by his last name. Even friends just called him Hardy. One of his best friends, one of his most famous mathematical collaborations was with the Indian genius Srinivasan Ramanujan. Ramanujan, they always called him just Hardy. Anyway, near the end of his life, not quite at the end, but after he had felt that he was sort of through with most of his productive work in math, he wrote this slim little volume called A Mathematician's Apology. And it's beautiful writing. I heartily recommend it to anybody who's going into math as something to read. It talks about the aesthetics of math, what makes an argument an elegant argument, and what makes certain arguments not so pretty, and why we should strive for the prettier arguments. He literally compared math to poetry and to art. And I think that's true, that math, when it's done well, can be extremely beautiful. This book is available at the Internet Archive. It's also something you can get for cheap because the copyright is long over. Um, but you can get a full text of it at the Internet Archive there. One of the things, sorry, before I talk about the proof, let me say a few things more about Hardy himself. He was a really, um, he had strongly held beliefs in, uh, well, against the war machine, right? He was a pacifist at a time when it was not popular to be a pacifist. So he was espousing pacifistic ideas during World War I, when the entirety of Britain was up in arms about going out to beat, you know, Germany and their allies. So that made him rather unpopular, even in academic circles in Cambridge and Oxford. He was viewed with distaste. He did not like the idea that any mathematics could be applied to activities that would harm people, that would get them killed. And part of what he says in A Mathematician's Apology is that pure mathematics, what he did was number theory, which is arguably the purest of math, or he also mentioned relativity theory. Those things would probably never be used to kill other people for centuries because they just didn't have that applicability. Well, he wrote this in, I think it was 1940, and World War II broke out shortly thereafter, depending on your chronology, slightly before. And World War II saw the use of number theory extensively in the British code breaking effort, well, the Allied code breaking effort to be able to hear what the Germans were communicating with their troops. They could listen in on the radio, but it was all encoded transmissions. So uh, hearing what the letters of a message were didn't make any sense. It was all garbled. The code breakers could ungarble it, and their tools were early computers and mathematics, and a lot of mathematics. So arguably, the British code breaking effort was the major factor in winning the war in Europe for the Allies. Um, Not to put anything against the brave people that sacrificed their lives on the battlefields, but their sacrifices were so much more effective than the German sacrifices because of the code breaking. Um, he had also mentioned relativity as a area that was too pure and thus wouldn't see itself used in warfare. And one of the central results of special relativity is E equals mc squared, which basically is that matter and energy are the same thing, just in different forms. C squared just being a kind of a proportionality constant between them. C is the speed of light, and c squared is a very, very big number because the speed of light is huge, right? So a little bit of matter turns into a lot of energy, and that's precisely what happened in Hiroshima and at Nagasaki. So yes, even relativity got used for mass deaths in the war just a few years after Hardy wrote his apology. One of the other things that he talks about quite a bit in his book is the concept of elegance, and I would argue the proof we're about to see is one of the primary examples of an elegant argument. It's quick, it's easy, it's like a great joke when you see the punchline. It's like, wow, it just comes together, and it's very beautiful. It's a moment of clarity and understanding. That's cool. The basic shape of the argument is what was known. Well, probably, actually, this is Latin, so I guess in the Greek they probably had another word for it. I don't know what that was, but we call it today arguing by contradiction, proof by contradiction. In the past, it was known as reductio ad absurdum, or reduction to an absurdity. How does that work? It's a little bit it's a little hard to learn to do this because you have to do something that's a little counterintuitive. You're going to assume that the very thing you want to prove is false. Right. Assume the thing you want to prove is false, and then argue from that perspective. From imagine you're in an alternate reality where the thing you hope is true is actually false. Pretend you're in that alternate reality and argue towards something that's absolutely ridiculous, something that can't be true. If you can show the falseness of your intended result is equivalent to something that's patently false, the falseness of a false thing makes the original guy true. Another element, I guess, of the argument we're going to see is that it's got a clean little piece of a sub-argument that we're going to need to deal with separately. And such little chunks of a proof that can be separated out and dealt with separately are often called lemmas. So this is one of a series of fairly bad math jokes that I plan to subject you to during these lectures. What's yellow and equivalent to the axiom of choice? Zorn's lemon. It's supposed to say Zorn's lemon. All right. Well, Zorn's lemma is a real thing. You learn about it if you take a course in analysis. And the axiom of choice is a real thing, and you learn about it as well. And it's true, Zorn's lemma can be used to prove the axiom of choice, and the axiom of choice can be used to prove Zorn's lemma, so they're equivalent. And just the random similarity of the word lemma and lemon gets you the joke. So now you know, like a grad student joke about Zorn's lemon. I'm sorry. So yeah, a lemma. A lemma is a result that is often proved only for the purpose of proving some other thing. That doesn't imply that it's like, of lower stature. A lemma can, like Zorn's lemma, actually is probably more important than the thing he invented it for in order to prove. But it does just means that it's your sort of original goal was to prove a theorem, and before you could get to that one, you had a little sub piece that you wanted to deal with. That's a lemma. So for the proof that we're going to culminate with today, we need a lemma that connects the evenness of a square to the evenness of the corresponding unsquared number. Let me throw this on the calculator. All right, so I'm going to try to use the calculator's table method to sort of let us explore this statement that we really should prove at some point. Basically, I just want to put in the function x squared. And we will look at the table. Why didn't it start at 0? Okay, so what I want to do is look down this list, and when I see an even square, figure out whether I'm dealing with an even x. So 0 is even, and the x next to it is 0, that's even. 1's not, but 4 is even. The number next to it is 2. So an even square, an even number. 9's odd, 16's even, and that's next to 4. So here's what we're trying to show, that if x squared is even, then x is even. The other direction of that is really easy. Can I show you that briefly? Suppose I wanted to show that if x is even, then x squared is even. Okay. If that's what I wanted to show, well, x being even, that means x looks like 2 times some integer k. Quick little piece of algebra says x squared is 2k squared, which is 4 times k squared, which is 2 times some other integer. It happens to be 2k squared. Right? But quickly you see that x squared is even. The problem is, this lemma we're after works in the other direction. If x squared is even, can you tell me that x is? If x squared is even, I guess I would need to take the square root somehow in order to get back to x, and that's not good, because if I'm taking square roots, I might leave the realm of integers. So it's hard to see how to use the definition in a straightforward way to go from evenness of x squared to evenness of x. But there is a technique, and the reason I'm sort of weaseling here about not wanting to show you the argument is it's really a good one for you to work on and to discover how that proof works. And I just don't want to steal the fun from you. So that's it set in symbols. For all x in the naturals, if x squared is even, then x is even. We explored it on a calculator. I could show you a CoCalc spreadsheet too. I made up this little snippet of code right here for x in range 60, so that's 0 to 59 are the numbers that will be involved. If what I did here is use the mod operator. In several computer languages, the percent sign is used for modulus. So that's x percent 2 is just like x mod 2. Well, if x mod 2 is 0, that's the same thing as saying you're even. So this is programmer shorthand for being even. And this would be x squared mod 2 is 0, so x squared is even. So if they're both even, I'm going to print them both. And you see what it did. It only printed every other one. All the odd x's are missing. And every even x involves an even square. Are there any even squares that are in between these things that go to some number that's not even? It's actually kind of easy to see that that's not going to happen. If you were dealing with an odd number in here, you could do a very similar piece, of algebra, and show that the square of an odd number is odd. So, all right, so except for at some point in the future, we should really set that, get that rigorously true. We should really prove that. Other than that, caveat, we're ready to make a proof. Oh, I just did Sage, so I don't need to follow that. Here's the argument. I've written it in the slides so that you'd have a record for it, but I think I'm going to pull up the version of it that's in the Giant book because it flows a little nicer there. But the theorem we're trying to prove is right here. Root 2 is not in the set of rational numbers. Whoops. That one. Okay, so here's the proof straight out of General Introduction to the Art of Mathematics. Let me reiterate how a proof by contradiction or reductio ad absurdum works. You start out by supposing the contrary of what you truly believe, what you hope to prove. So we think root 2 is actually not a rational number, so we're going to argue by assuming that it is. Then we have this really sort of perverse goal in mind, I can imagine. You've got to now argue intentionally towards something that's completely, got to say this in a clean way, ridiculous. It doesn't make any sense. It's something that's clearly false, in fact. So, yeah. All right, so let me try to read it to you. Suppose to the contrary that root 2 is a rational number. Then, by the definition of the set of rational numbers, we know that there are integers a and b having the following properties. There's a third property that b is non-zero. I don't really need that one for this argument, so I've left it out. But root 2 is a over b, and the GCD of a and b is 1. They're relatively prime. Now we just consider the expression root 2 is a over b. That's fine. Often, proofs have a little bit of a follow your nose kind of feeling to them. You're looking at this equation, root 2 equals a over b, and you know that root 2 is problematic because it's not an integer. You can do stuff with integers like even and odd and things, but root 2, it's a real number. Or I guess in this world we think it's a rational number. But if you square both sides of this, which is legal, right? You got an equal sign between two things. Two things are equal, then their squares are going to be equal. This is what you get. 2 is a squared over b squared. Okay. And now we're dealing with all things that are whole numbers. 2 is a whole number. A squared and b squared are whole numbers because by assumption a and b are integers. And we can solve that or rearrange it so that a squared is written as twice b squared. This is where our lemma shows up. An immediate consequence of this last equation is that a squared is an even number. You see it, that a squared is 2 times something else? Using the lemma, we now know that a is an even integer. And hence, that there is some integer, let's call it m, such that a equals 2m. Substituting this, a equals 2m, into the previous equation gives, see, the previous equation had a squared on the left and then b squared, 2b squared on the right. We've got 2m squared now. We just replace that a with 2m. That's legal. That's called substitution. You have two things you know are equal. You can switch them back and forth. This is just algebra. We square 2m and we get 4m squared. And you see how there's both sides of this have a factor of 2, so we cancel that off. So 2m squared is b squared. Well, what does that tell us? Oh, this tells us that b squared is even, and hence, using the same lemma, that b is even. Now, that actually is the absurdity. The reason that's absurd is that if both of them are even, if a and b are even, then the smallest their GCD could be is 2, because 2 is certainly a divisor of each of them if they're even. But on the other hand, we had the initial assumption that those numbers are relatively prime, because our definition of rational numbers includes the idea that they can be represented in lowest terms. So do you see how these are contradictory things? GCD of a and b greater than or equal to 2 can't exist in the same world where the GCD of a and b is equal to 1. They say different things. Right. So that's a contradiction, which means our original assumption is false. Just unwinding that a little bit, our original assumption was that what we really wanted to prove was false. So that means what we really wanted to prove is true. Root 2 is not a rational number. So a couple of comments about formally writing out proofs. When you begin a proof, let your reader know that you're moving off of ordinary language and into this sort of crystallized, very careful kind of speech that you use in writing proofs. So I usually, and this is probably the most typical way to start a proof, write the word proof in italics and have a colon. Let them know that this is, stylistically a different thing. And also let them know when you're done. This marking here and pushed over to the right-hand side is kind of old school. It's QED stands for quod erat demonstrandum, which is Latin for basically that which was to be shown, or that which was to be demonstrated. I had a student once who, very, very bright young guy, who objected to using QED at the end of a proof by contradiction, because you in fact haven't done that. You have reached a place of confusion and said, oh, well, because of this confusion, it means the original assumption that our desired result is false is wrong, and therefore our desired result is true. QED isn't quite the right thing. We haven't done what we set out to do in a straightforward manner. And so he came up with the initialism QISE, which I don't remember the second word, but I think it might have been idem. Quod idem stercus. It's the Latin word for shit. So what is this shit? Quod idem stercus est. I think that's right. And so he continued to write QISE at the ends of proof by contradictions and QEDs at the ends only of direct arguments. The kind of thing I did over here on the thing is, well, that's an outline of a direct argument. Neither of those, particularly the QISE thing, he was kind of being a smart ass. But sorry, Mike, if you're ever watching this. What most people do these days is actually make something that looks a little bit like what I've done by highlighting They're just a colored in rectangular block at the end of the proof. It kind of doesn't matter stylistically what you do, as long as you do something consistently in your work so that people know here's the beginning of a proof and here's the end. Because sometimes, it's easy to space out a little bit and you're reading along and you go, wait, what? I just reached the end of the proof? What happened? And you have to back up and figure out what happened. It's good to mark that sort of transition off to your readers. Okay, I believe we have reached the conclusion for today. Let's see if there's any more slides. Well, that's the end of the proof. And no, that's the end of the slide. So great. So that's the conclusion of Lecture 6. Thanks for sticking it out to the end. And hopefully I'll see you on Lecture 7. Have a great rest of your day. Just a quick little postscript. Here's the icosahedron finally put together using those magnetic toys. I also, once at the joint math meetings, found one of the booths. They were selling all the platonic solids, carefully cut, actually I believe machined or sawn anyway, out of beautiful wood, Japanese maple. And this is the icosahedron. Actually, got the full collection, but that's the one that was a secret to the Pythagoreans. D20.